What specific problem does the new method GECKONUM aim to solve in the context of text-to-image models?
The new method GECKONUM aims to solve the specific problem of evaluating numerical reasoning in text-to-image models. It addresses the gap in existing benchmarks by providing a comprehensive and controlled benchmark that focuses on assessing different aspects of numerical reasoning, such as exact number generation, approximate number generation, and reasoning about partial quantities. GECKONUM is designed to evaluate how well text-to-image models can accurately generate images based on text prompts that contain numbers and quantities, which have been challenging for existing generative models. By formalizing evaluation as 3 tasks and designing various template types to control for different variables like sentence structure, context, and the number of attributes entities in a prompt, GECKONUM provides a systematic way to measure the numerical reasoning capabilities of text-to-image models.
How does the proposed method GECKONUM work, and can you illustrate it step by step?
The proposed method GECKONUM works by providing a comprehensive and controlled benchmark of text prompts aimed at evaluating different aspects of numerical reasoning in text-to-image models. It formalizes evaluation into 3 tasks: exact number generation, approximate number generation, and reasoning about partial quantities. The method consists of 1386 text prompts, 52,721 generated images, and a total of 479,570 human annotations. 1. Task 1. Exact number generation. This task evaluates a model's ability to generate an exact number of objects specified in a prompt. It includes various prompt structures such as numeric simple, numeric sentence, 2 additive, 3 additive, attribute color, 2 additive color, and attribute spatial. The task examines factors like number magnitude, number representation, digits versus words, and noun frequency in English to assess model performance. 2. Task 2. Approximate number generation and 0. This task evaluates models on their ability to depict entities with quantities expressed in approximate terms using linguistic quantifiers. It also assesses how well models interpret the concept of 0. Prompt types include approximately 1 entity and approximately 2 entity, testing models on generating approximate quantities and understanding 0. 3. Task 3. Conceptual quantitative reasoning. This task evaluates models on prompts that require a conceptual understanding of objects, parts, proportions, and fractions. Prompt types include fractional simple, fractional complex, and part whole, challenging models to reason about fractions and relationships between objects. GECKONUM also involves human annotations collected from study participants for each task. Participants count objects in images, select descriptions that best match images, and answer questions related to the prompt words. The method then processes these annotations to calculate model accuracy based on the agreement with the ground truth. Overall, GECKONUM systematically evaluates numerical reasoning in text-to-image models by providing a diverse set of prompts, assessing different aspects of numerical cognition, and utilizing human annotations for model evaluation.
What are the theoretical or practical benefits of using GECKONUM for evaluating numerical reasoning in text-to-image models compared to existing benchmarks?
The theoretical and practical benefits of using GECKONUM for evaluating numerical reasoning in text-to-image models compared to existing benchmarks lie in its comprehensive and controlled nature. The paper highlights that existing benchmarks lack a comprehensive evaluation of numerical reasoning due to limited prompts with numbers and numerical concepts. GECKONUM addresses this gap by offering a vast dataset covering various dimensions of numerical reasoning, such as different number ranges, types of nouns, representations of numbers, linguistic quantifiers, and reasoning about partial quantities. This thorough evaluation allows for a more accurate assessment of a model's numerical reasoning capabilities across different aspects, including exact number generation, approximate number generation, and conceptual quantitative reasoning. Additionally, GECKONUM's diverse prompt types and templates enable the evaluation of models on a wide range of numerical tasks, providing a more nuanced understanding of their strengths and weaknesses in handling numerical concepts in text-to-image generation. Overall, GECKONUM's design allows for a more robust and detailed evaluation of numerical reasoning in text-to-image models, making it a valuable benchmark for advancing research in this area and driving improvements in model performance.
How were the text-to-image models evaluated using GECKONUM and human annotations?
The text-to-image models were evaluated using GECKONUM and human annotations by generating images for 7 models from 3 different families, including DAL E3, Imagine, and Muse. A total of 1386 text prompts were used, resulting in 52721 generated images. Human annotations were collected to measure if the images accurately matched the prompts in terms of numerical reasoning. For Task 1, exact number generation, participants were asked to count the number of objects in each image generated by the models. For Task 2, approximate number generation, participants selected the line that best described the image out of 3 to 5 lines of text. In Task 3, conceptual quantitative reasoning, participants answered a series of short questions based on the prompt using an automatic question generation approach. The annotations were processed by standardizing the format and encoding them for comparison with the ground truth numbers in the prompts. The accuracy of the models was calculated based on how well they matched the human annotations, with the ground truth numbers from the prompts used as a reference point for evaluation. Each image was annotated by 5 participants, and a high level of inter-annotator agreement was observed in over 96% of cases, ensuring consistency in the evaluation process.
What were the overall results achieved with GECKONUM in terms of model performance on different tasks?
The overall results achieved with GECKONUM in terms of model performance on different tasks showed that Task 1, which examined the model's ability to generate an exact number of objects, was the easiest for all models. DAL E3 outperformed other models by a large margin on Task 1, followed by Muse B and Imagine D. However, even the best-performing model's accuracy was still below 50%. Task 2, which evaluated models on their ability to depict entities with quantities expressed in approximate terms, showed that prompts with fewer entities were easier than prompts with 2 entities. Models struggled with understanding linguistic quantifiers, such as no, as generating images with 0 objects was particularly challenging. Task 3, which focused on conceptual quantitative reasoning, was the hardest for models, with most models performing close to or below the baseline. 6 out of 7 models had the highest accuracy on fractional simple prompts, indicating that understanding concepts like fractions and proportions was challenging for the models. Overall, the results demonstrated that while DAL E3 was the best-performing model overall, there were instances where other models outperformed it on specific prompt types.
What are the limitations or drawbacks of using GECKONUM as an evaluation benchmark for numerical reasoning in text-to-image models?
The limitations or drawbacks of using GECKONUM as an evaluation benchmark for numerical reasoning in text-to-image models include 1. Complexity of prompts. The prompts in GECKONUM are designed to be comprehensive and cover various dimensions of evaluation, which can make them challenging for models to interpret accurately. The complexity of prompts, such as including multiple numbers, spatial relationships, and color terms, can impair the ability of models to generate images correctly. 2. Lack of clear ground truth. Evaluating models on Task 3, which focuses on conceptual quantitative reasoning, is more challenging due to the lack of clear ground truth. This can make it difficult to assess model performance accurately, as some prompts may not have a definitive correct answer, leading to ambiguity in evaluation. 3. Model performance variability. The performance of models on different tasks within GECKONUM can vary significantly, with some models excelling in certain prompt types while struggling with others. This variability can make it challenging to compare models consistently across all aspects of numerical reasoning. 4. Limited generalizability. The findings based on the evaluation of models using GECKONUM may not generalize to all text-to-image models or real-world scenarios. The dataset may not capture the full range of challenges that models may encounter in practical applications, limiting its generalizability. 5. Interpretation challenges. Some prompts in GECKONUM may require a combination of different reasoning skills beyond numerical reasoning, such as spatial understanding or color recognition. This can make it difficult to isolate and evaluate numerical reasoning skills specifically. 6. Scalability. As GECKONUM consists of a specific set of text prompts and associated images, its scalability to accommodate a larger and more diverse set of data for evaluation purposes may be limited. This could restrict its applicability to a broader range of text-to-image models. 7. Human annotation variability. Despite efforts to ensure inter-annotator agreement, there may still be variability in human annotations, which can introduce noise and uncertainty in the evaluation process, affecting the reliability of the benchmark results. 8. Model-specific challenges. Certain models may perform better or worse on specific types of prompts within GECKONUM, leading to potential biases in the evaluation results that may not reflect the overall performance of the models accurately. 9. Need for additional evaluation metrics. While GECKONUM provides a comprehensive benchmark for numerical reasoning evaluation, additional evaluation metrics may be needed to capture nuances in model performance that are not fully addressed by the current benchmark. 10. Training data bias. The use of synthetic data in GECKONUM for training VLMs may introduce biases or limitations in model performance evaluation, as the models may not have been explicitly trained on the dataset, impacting their ability to generalize to new tasks or datasets.